Hi guys, welcome back to Data Every Day. Today we're looking at a data set of weather in Seattle from 1948 to 2017. And we're going to try to predict, well, the data set says how did it rain in Seattle? So it's sort of expecting that we're going to try to predict the rain column. It says, can you use this data set to build a model of whether it will rain on a specific day given information on the previous days? Um, and if you look, this rain column is actually, it was formed from the precipitation column. So if we go ahead and try to do that, if we try to predict rain, we're going to easily get 100% accuracy simply because this was produced by a function of the data, right? So um, I'll actually show you, but I think in the meantime, what we should rather do is try to predict the precipitation. Now, I don't know how well we'll do because we don't have a lot of data here. There's only 5 columns. But let's try to do a regression task and predict the actual precipitation value for a given day. So let's hop into the notebook. We'll use a variety of regression models to make our predictions. So I'm importing NumPy and Pandas just for working with the data. Then I'm going to use Matplotlib and Seaborn just for visualizing some of the correlations between the features. And then we'll use the train test split function and standard scaler from sklearn for preprocessing. Then here are all of our regression models. So we have quite a few. I just want to see what will do the best given this limited set of data. And then afterwards, I'm going to try to predict the rain column, like the dataset asks, using a support vector classifier, and then I'll just use the accuracy score metric to evaluate the performance. Alright, so let's actually load in the data using pandas.readcsv. We can get the file path over here. So I'll grab the file path and then paste it in, and we can take a look. Oh, I didn't actually import these. Okay, there we go. And I will load it in and we'll take a look at the data. And so we have 25,000 rows and only 5 columns. However, we do have some date information which I would like to use to create 3 new columns, one for the year, one for the month, and one for the day. Additionally, let's check for any missing values. We can check with data.info. And we can see we have a few missing values here. It looks like a really insignificant amount though. And we also have just 2 object columns, which will be the date and the rain column. So let us begin pre-processing. And I'm going to create a function called preprocess inputs. It's going to take in a data frame. It's going to make a copy of the data frame. And then at the end, it will return that copy. So currently, all this will do is return the same data frame we pass in. So if we have data on the top, and then I'll call the processed version of data x. X will be preprocess inputs of data. And we can look at x. Currently they're the same, but now as I add into the function, we can see the results down here. So the first thing I want to do is let's deal with the missing values. So let's actually take a closer look how many we have. Data.isNA will give us that. Well, this actually gives a true-false matrix and a true corresponding to a missing value in a given location. So if we sum over the row axis, then we'll get the total number of missing values in each column. And you can see out of 25,551 examples, we only have 3 missing values. I'm not sure if they're in the same rows or not, but this is a very inconsequential number of missing values. So I feel like maybe we can just drop these records. It's really not going to affect it very much, since 3 to 6 rows is really inconsequential. So df equals df.dropNA. So we'll drop any missing values from the data frame along a specified axis. The axis we're going to use is 0, which is the row axis. So we're dropping any rows with missing values. And because we're dropping rows, the indexes will go missing from the values we drop. So I'm just going to reset the index afterwards with reset index. And I want to include drop equals true there. so that we don't use the old indices as a new column. Alright, let's run this and take a look at x. Okay, so we have 3 fewer rows. So it looks like there were actually just 3 rows with missing values. So that's not a big deal. We still have most of the data here. And the next thing I want to do is actually change this column into a numeric column. So when you have a Boolean column, it's extremely simple. Let me say drop missing rows. But when we have a Boolean column, it's extremely simple to convert it to a numeric. All we have to do, convert rain column to numeric. All we have to do is take rain, df sub rain, and set it equal to df sub rain dot as type numpy dot int. So this is just a type conversion, and the trues will go to 1 and the falses will go to 0. So if we run this, you can see we now have 1s and 0s instead of trues and falses. Alright, and the last thing we really got to do is deal with this date column. I want to extract 3 features from this column. I want to take a year, a month, and a day. So to do this, we can use the toDateTime function from pandas. So if we look at the date column currently, the data type is object. So these are actually encoded as strings. But if we call pandas.toDateTime on this column, it will return the same column, but in the data type is now a datetime object. And what's nice about a datetime object is we can actually now apply a function to this column where x represents a given entry, and we'll map x to x.year. So now we can actually just get the years because it is a datetime object, and then we can get the months like that and get the days like that. So we can get these integer features out of the date object just by converting it first to datetime. Alright, so up here let's do that. Extract date features. So first we're going to turn it into datetime. So df sub date equals df sub date, and I just want to turn this one into datetime. So pandas.toDateTime. Okay, now we can go and create those 3 columns that we want: year, month, and day. So let's call one of the columns year, and the year column is going to be just taking the date column and applying a lambda function to it, where x is a given entry, and now because it's already in datetime form, we can just get x.year, and now every date will get mapped to its corresponding year and then stored in the year column. And similarly, I want to do that for the month and day columns. So this will be month, and this will be day. And then over here, we just say x.month and x.day. Alright, now we can take a look at x. And you can see we now have year, month, and day, which are just the values taken from the date. So now we don't need the date anymore, so I'm just going to go ahead and drop that. So df equals df.drop date from access1. We're dropping from access1. And now you can see our data is fully numeric. The only thing left to do is split off what we're trying to predict and then scale the rest of the data. So let's split df into x and y, where y is going to be what we're trying to predict and x is the remaining data. So here we're trying to predict precipitation. So I'm going to say y equals df sub precipitation, or PRCP, and x is going to be everything except PRCP. So I'm dropping it from axis 1. And now what we'll do is return x and y instead of just df. So we'll get that over here, x and y. And if we look at x, it should no longer have the precipitation column, but that has been stored in y. So now we can see we have separated it. And the reason we'd like to do this is because now we can scale this data and just work with this as the features and then this as our target. So let's scale x. And so scaling will give each column a similar range of values to the others. And before I scale it, I actually do want to do a train test split. So we're going to allocate like 70% of the data for the train set, and the other 30% will be in the test set. So we can do that with the train test split function, passing in x and y, and specifying the size of the train set, so 70%. And this will also shuffle the data by default, which we do want to shuffle the data anytime we feed it into the model, but this will do it for us. And because we're shuffling, I want to include a random state that will ensure the shuffle is always done in the same way. And so this function will return 4 new sets of the data: xtrain, xtest, ytrain, and ytest. And now let's return those 4 values instead of just x and y. So return all those 4, and we'll get them over here. And let's take a look at xtrain and ytrain. So here's xtrain. You can see they've been shuffled, the indices, and then we also have only 70% of the data here. If we look at xtest, we have the other 30%. But what's important here is that the indices are matching up. So these are the targets for the shuffled data. And then I guess over here we'll say predicting the precipitation column. And let's see. So we want to train a whole bunch of models on these. I guess actually we should do the scaling. So I'll create a scalar, which is standard scalar. That's from sklearn. Standard scalar will give each column a mean of 0 and variance of 1. So I'm going to fit the scalar only to the train set, because we want to sort of assume we only have access to the train set at the time of preprocessing. And I'm going to transform both the train and test sets using the fit to the scalar that I got from the train set. So we can do that with scalar.transform, passing in here xtrain and here xtest. And I would like to note that this returns a NumPy array, so I want to convert it back to a data frame, like so. And I want to specify the column names. I want them to stay the same as x.columns. Alright, so now if I return these, you can see this was our original data, but now if I have it scaled, you can see that each column now has a similar range of values, and y is unscaled. If we look at the means of each column in xtrain, you can see they're all extremely close to 0, and if we look at the variances, they're all extremely close to 1. So this is ready to go into our model. And so I'd like to create them here. I guess we can bring this down actually. Alright, so we'll make a whole list of models. I don't want to declare each one of these models in their own variable, so I'm just going to put them all in the list, or rather actually a dictionary I'll put them in. So we'll make a dictionary of models that's going to map the name of the model to the actual instance of the model. So I'm passing this in, and I'm just going to go in and remove all of these import statements so that we're just left with the model names. Let me just grab all of these. Alright, and delete. Oh no, I forgot 2 of them. Alright, then we'll just put, I don't need logistic regression. That shouldn't be there. Let me remove that. That is a classification model. Okay, and let's put each one on its own line. And then I'm going to give each one a name. So what I'll actually do is I will map it to a name, and then, right, so the name is mapping to the actual instance, and I need to actually construct these models and put commas. And so I'll indent this over 1, and now we have an index. Now I just want to put the names of these in. So this is linear regression, just a simple linear model. Here is ridge regression, or L2 regularized linear regression. This is k-nearest neighbors, just a simple algorithm. Decision tree class regressor. So decision tree, linear support vector machine. So it's a support vector machine with a linear kernel, and this is a support vector machine with a nonlinear kernel. In this case, we'll be using an RBF kernel, or radial basis function kernel. This is a neural network. And then here are our ensemble methods. The first one is a bagging technique, and the following ones are boosting techniques. And the difference is in bagging you have a bunch of models being constructed in parallel, and in boosting you have models constructed in series. So this is a random forest. This is gradient boosting. This is XGBoost, or extreme gradient boosting. This is light gradient boosting machine, or light GBM. And this is cat boost. Alright, and then all I want to do here is add in, I actually want to sort of space these so that they all line up. And this will be really nice so that we can, so that we can visualize all the R squared values right next to each other. So I know this is very tedious. You can definitely skip past this if you don't like watching. I'm very sort of OCD about getting all these lined up. Yeah, let's actually just grab all these. Oops. Okay, there we go. So now they have spaces at the beginning, so we can print out all the scores of each model next to each other. And now we have this dictionary, so I want to fit each one of these. So for name and model, in models.items, so models.items will return the key value pairs of the dictionary as tuples, which we can then iterate through 2 at a time like this. And I want to train each model, so model.fit on the train set. And then I want to print out just a statement that says each model has been trained. So run this, you can see each model is being trained, and it should not take too long. We don't have that much data, certainly not that many columns, but it might be taking a while because this is a hard fit to do. There's really not much information in this data set for predicting the precipitation. Oh, did we run into an error here? Oh no, it's cat boost. Cat boost needs an extra little argument to keep it from showing all this stuff. So I'll keep it on verbose 0 and I'll retrain those. Yeah, I just want to point out that we're trying to predict precipitation given only the year, month, day, whether or not it rained on a given day, and the minimum and maximum temperatures on that day. So it's not really a lot. Maybe if we had humidity, it'd be okay. I don't know. This is not a lot of information. So I doubt we're going to get really good results here, but let's see. So we've trained all our models, and now for each name and model in models.items, let's print out the R squared score for each classifier. So R squared, sorry, it's not classifier, it's a regressor. R squared score is a measure of how dispersed the data is around our fit. So it's a measure of how well the regressor has done at creating a proper fit to the data. So name plus R squared. Actually, I'll put, okay, I won't even put, I'll put R squared. Name plus R squared colon, and then let's format it to 5 decimal places and pass in model.score xtest ytest. So the score function for regressors in sklearn will return the R squared value, which will then get plugged in here. So let's take a look at each one. And we can see that these are not very good. The worst one is definitely decision tree. We actually have a negative R squared value here. And our best one seems to be the gradient boosting. And it looks like maybe some of the ensemble techniques did well. Our neural network did well as well. But especially the linear model, the linear kernel SVM didn't do so well. And so this isn't really a surprise. Like I said, there's not a lot of information here. The highest value an R-squared score can take is 1. And this isn't terrible. Like, we still have some predictive power in this. But it's definitely not perfect. So now I want to show you what happens if we try to do the original task that this dataset suggests. So yeah, let's try this. Predicting the rain column. So the rain column is just this binary column, 0 or 1. Before we scale it, it looks like true or false. And we're going to try to predict whether or not it rained on a given day based on the other features. And like I said, this should be extremely easy because this is actually encoded already in the precipitation. If you look, this will always be true if we have a value greater than 0, and it's only false in the case where precipitation is 0 exactly. So this really should not be difficult. Let's grab this function, and I'm just going to sort of make a modified version of it down here. We'll call it preprocess input CLF for classifier. And so we still want to drop the rows, and we want to convert the rain column. And we'll keep the date features, and we will except here when we split, y is not going to be precip, y is going to be rain, and x is going to be everything except rain. So now if we do it exactly the same way, this time we do have to use a classifier instead of a regressor because this is no longer a regression task. If we look at our xtrain now, well, actually I have to get the values. So these guys are going to come from preprocess inputs CLF, which is the name of this function, and we're passing in data again. And then let's take a look at xtrain. You can see we now have the precipitation column as a feature, and our y-train is going to be this classification column of either 0 or 1 that we're trying to predict. So let's see what happens. I'm just going to create a single model, I'll call it CLF, and I'll make it a linear SVC, so linear support vector classifier. So it's a support vector machine with a linear kernel. So it will try to find a linear fit to the data. So let's fit it on the train set. And then we'll print out the test accuracy. So this time it's an accuracy value. So let's display that to 2 decimal places with a %, and format that with clf.score evaluated on the test set. So the score function for a classifier will return accuracy. And we have 100% accuracy. So this isn't a surprise. Actually, I have to multiply this by 100 since it is an accuracy value. 100%. So yeah, this, like I said, all the information we need to predict this with 100% accuracy is right in this column. So in fact, if we go up into our function and remove the date features altogether, and then we're dropping all features except precipitation. So if we are only using the precipitation column, so that means we're going to drop date, we're going to drop Tmax, and we're going to drop Tmin. If we drop everything except precipitation, then our xtrain is a single column. Our y-train we're still trying to predict, but using only a single column. If we try this, we actually get 100% accuracy. So yeah, I mean, this is this is why this task doesn't really make sense, because there's a clear linear relationship between here. Actually, is it linear? That's a good question. Let's actually examine something. Let's examine the correlations. I want to know if it's a linear relationship or not. So I want to see the correlation values for the data. And so what I'll use is, instead of using this xtrain, I'll use the original one, this guy. So I'll save xtrain in here. This is just the original values like this. And I want to get all the correlations for this along with the Y-train as well. So I'm going to put Y-train on the side. And we can do that by creating a correlation matrix, by concatenating the X-train and Y-train back together. So we split them, but now we're putting them back together, concatenating them on axis 1, so side by side, and then getting the correlation matrix from that with .core. So if we look at this, these are the correlations, and we can actually visualize it a lot nicer by using a seaborne heat map. So let's create a new matplotlib figure. Fig size can be 12 by 10, and then sns.heatmap, and passing in core. I'm going to turn on annotations and set the minimum value that we can on the color bar to -1.0, and I'll give it a C map of Mako. Alright, let's take a look at that. And so we can see this is the precipitation column, this is the rain column. Alright, and if we look at this, the correlation between precipitation and rain, which is this right here, is not very high. It's not a strong correlation. And so these are measures of linear relationships in the data. And so it looks like there actually is not a linear relationship between precipitation and rain. It's interesting. If we go back down here now and pre-process them this way, let's try not scaling it. Okay, I'm going to take the scaling off. So we're just going to use the original X-train values, this are original precipitation values, along with the the ones or zeros depending on if it's a zero or not. Then you can see, okay, we actually didn't get 100%, because even though it's a very simple relationship, it's not a fully linear relationship. However, if we change this to a proper support vector machine with a radial basis function kernel, so it's now capable of modeling nonlinear relationships, then we should get 100%. And in fact, if we look at, let's see, using or classifying using a simple function. So I'm actually going to try to classify the rain based on just a simple function instead of using a machine learning model. So we can create a set of predictions, ypred, which will basically just be xtest. So here's our test set. And in this case, xtest looks like this. It's just precipitation values. So we're going to ask, is xtest greater than 0? We'll get trues and falses. And all you have to do is turn that into a NumPy array, casting the data type to integers. And now we'll get ones and zeros as our predictions. I'd actually like to squeeze it down. Actually, we can do it this way. NDmin, which is minimum dimension, will be 1. Or no, 2. I'm confused. Usually this works. 0. Nope, not working. Okay. So we'll just squeeze it then. Because you can see there's arrays inside here. I don't like that. I just want to make sure it's the same dimension as our actual test set, our y-test. So that's our y-test, and then our predictions given by just this simple function right here. So what I'll do is ypred is equal to xtest greater than 0, and ypred equals numpy.squeeze numpy.array ypred, with the data type being numpy.int. And so down here, you can see our xtest looks like this. So we're just going to basically create a classifier using just this function. And now if we look at the accuracy score, so let's print out test accuracy. And I'll display this to 2 decimal places again with a %, except this time we're passing in the accuracy score. So this is just the metric from sklearn that I imported, and we're evaluating that on the test set with our set of predictions that we got just from this function. And we'll multiply it by 100 because it's an accuracy value. And you can see we have 100% accuracy without even using machine learning. So this is a reason that you have to be careful in what features you're using if you're predicting something. So someone might look at this and say, wow, my model's doing extremely well. It got all of them correct. But then you take a closer look at the data and you see there's this very simple relationship between the correct answers and the test data. And in fact, we're only using a single column here and getting 100% predictions. That will sum up today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.